Morning, everybody. Going to lecture here for a bit, and then we'll get into the lab. I need to teach you about telescopes and microscopes, and then you'll be building those devices. So that actually lined up really, really well. If you would please pass down these magnifying glasses, brand new ones, and they're plastic, right? If you would mind unwrapping every single one of them that's at the table, please. And disposing of the plastic. I'll send this around to put them away when we're done using them, but yeah, you get the brand new ones today. Fancy. A couple other things. I fixed the calendar for the rest of the semester to account for my inability to teach quickly and often. I've forgotten to update the homework due dates, but those are all fixed as of this morning. I even noticed the chapter 43 homework wasn't a thing, so I can sign that.
Test on the 21st.
Yeah, I needed the thing. So, on campus.
Yeah.
Okay, well that doesn't actually matter.
No.
Okay, but thank you. I'll change the test date. I put those test dates in there only for you guys. So as long as it's striking fear into your heart, it's still working.
The test office is 34 to 36, but it's on 33 as well.
So fixes need to be made. This is surprising. Okay. Especially with me. What's the other thing? I got an email this morning saying that the district has enabled you to go into My Portal and change your preferred name and pronouns.
I got an email about that yesterday.
So those of you that use like your middle name or a nickname or have a different name or have pronouns that you prefer, you should be able right now to go to My Portal, and they said click like on your name, like your account name that's up in the corner. There should be options in there for you to do that. So that helps me, okay? Because on the roll on Canvas it gives you your legal name, but maybe you go by a different name and I can never find you when I'm grading papers, right? So yeah, if you do that, then it should carry over into Canvas and any attendance systems that your teachers may use. So like next semester on first day, we should be getting the roles that have the preferred names instead of the actual legal names. So I encourage you to do that, right? Just to not only help yourself out, but help the teachers out with calling you the way you want to be called. All right, let's see here. So before I teach you about telescopes and microscopes, we're going to talk about what it means for something to appear closer than it really is. What kind of image is being formed in this diagram here on the right? It's a virtual image. So where does it form? In your brain, right? Okay. We say that the image forms at whatever distance we calculate the image distance to be, but really it's forming in your head. And so basically, every telescope, microscope, pair of glasses, whatever, we're dealing with, well, in the case of a telescope, well, we'll get there. We're dealing with a perception, okay? And when we say something looks big, okay, or looks magnified, what we're trying to describe is it's not the size we expect it to be. So grab your magnifying glass, okay, and if you haven't unwrapped it yet, do unwrap it. Are these easy to unwrap? Or? Yeah.
There's a little pull tab on the bottom.
Apparently I'm unable to, okay, look at this plastic thrown right here. Take your magnifying glass out of here, okay? Well, the little one too. Wow. What? Okay, good. I'm going to be able to teach you something else that I didn't realize. If you take this magnifying glass, don't look through the little one right now. Just look through the big one, okay? You look at something up close. Look at your nose, look at a piece of paper, look at your hand. Just look at something, okay? Describe to me whether that's magnified or reduced.
Magnified.
It's magnified, and it's right side up, okay? So, why are you saying that it's magnified? What are you seeing? What are the clues that this thing is bigger? Well, there are distortions, but these are cheap magnified. It's closer? Why are you saying it's closer? your brain thinks it knows how big a hand should be, or a thumbnail, or a piece of lettering on the page, right? You're making a comparison between what it looks like in reality to what this virtual image that's forming in your brain looks like. And so we see things as being bigger when they take up more of our field of view. So when we're looking at the actual object, say over here, right, it's small, right? And we say it doesn't take up very much of the field of view. But as I bring things closer, okay, like my hand far away only takes up maybe 10% of my field of view, right? But as I bring it closer and closer to my face, my hand becomes the dominant thing, right, in my field of view. It's taking up a lot of my visual field. And so when we generate a virtual image that's taking up most, right, of your field of view, we say it's bigger, magnified, closer. It's a perception it's a comparison based on perception. Let me give you some other examples, right? And by the way, for those of you that couldn't work the magnifying glasses, right? Okay, we know that the word Mississippi isn't that big. And so because it appears bigger, because it's taking up more of our field of view, we say that it's magnified or that it's closer. So if we went outside, maybe not right now in the rain, but we looked down campus, right? We looked from this building all the way down to the fountain that's down there, right? How big would the people appear who are standing around the fountain? They'd feel really, really tiny, right? So what does our brain assume about those people? That they're far away. Why does it assume they're far away? Why doesn't our brain say, well, they're just small people? We know the fountain's far away, but more importantly, right, I can stand over here, okay, and Matthew appears a certain height in my visual field, and as I get closer to Matthew, more and more of Matthew is taking up my visual field. And I'm standing close to Matthew, so this must be the size of Matthew, right? But you did answer, right? But if I come over here, I have had this experience, right, of being that close and knowing his actual size, right? And now his size doesn't match with what my brain has learned to be his real size, and so I don't say Matthew shrunk. I say Matthew is further away, which is compounded by the fact that I did traverse actual space and time, right? So I'm not saying your perceptions are false. I'm just saying our brain chooses to interpret really tiny people over there to be far away people instead of being tiny people. So we can leverage that perception, right, to make things that are really, really tiny far away appear closer and bigger. If I want to look at a galaxy that normally would be a little tiny pinprick on the night sky, I can make it appear both closer and bigger by taking advantage of these perceptive things, right? By changing how much of the field of view that galaxy takes up as I look through a telescope. But let's talk about microscopes first. They're the harder of the two. And what's going on in both telescopes and microscopes is that we have a compound optical system. By that we mean there's more than one lens in it. So compound systems are two or more lenses in the optical system. And when you have two or more lenses together, you can do two things. First of all, you need to run a lot of calculations, and what ends up happening, okay, is whatever image is formed by the first lens becomes the object of the second lens. I'm not going to make you do this today. You're not going to have to calculate and do any ray diagrams and do any thin lens equation stuff. I'll make you calculate magnifications. But let me give you some terminology that is used throughout optics when it comes to compound systems. The lens that is closest to the object in your stack system is always called the objective lens. Objective because it's the object lens, right? And then the lens that, and there could be any number of lenses in between, but the final lens, the lens that is closest to the eye, right, where you're looking through, is called the eyepiece. Again, because it's close to the eye. So you'll hear me refer constantly over and over again today to your objective lens and your eyepiece, or maybe just the objective and the eyepiece. Notice in this diagram that they've done for us, right? Okay. The object for a and what's a microscope supposed to do?
Magnify.
Magnify what? Very close, tiny things. Which is different from a telescope. A telescope does what? Magnifies usually very large things that are far away. By definition, galaxies are bigger. Okay. So the microscope, we're taking a very small object and we are trying to make it appear larger. But it is also very close to the lenses in our system. Anybody take a biology class and use that microscope, you've got those different lenses that you can turn, and you start with sort of a low power one to get, and then you kind of zoom in as you change the focal length. What's going on there, in a microscope, you want your object to be really as close to the focal length of your objective lens as possible. The closer you get this object to the focal length, the bigger this image will be. Now, it's a converging lens on here, right? And as long as we're outside the focal length, what kind of image are we going to get? It's going to be a real image, okay? And so the closer we get this, the bigger that real image becomes. But then we're using a converging lens. And the image formed by the objective is inside the focal point of the eyepiece. That image is now the object for the eyepiece. What kind of image are we going to get? A virtual image. Now, the real image is flipped. And since the virtual image doesn't flip, it still appears flipped. That's why in biology class you struggled. You move the slide to the left and everything like that. Okay? You can thank optics. Or the designer of the microscope, because they just didn't put one more lens in there to flip it. Anyway, I was always clear about that. So, key things in a microscope, okay, are to get the object as close as you can to the focal point and still be able to image the thing. You can get really close to the focal point and the image is so large that your system is unable to resolve it. So today, you're going to be fooling around with that. Okay? You're going to be fooling around with where do I put my object in relation to the objective lens in your system. And there'll be some wiggle room there, okay, as you guys fight and decide over how much magnification can we get out of this system. So, but key thing, object close to focal length of objective, and then the eyepiece, right? You're always putting that image that's formed by the first lens inside the focal length of the other. So you have a ballpark, right? If you know that you're working, say, with a 40 centimeter objective lens and a 20 centimeter eyepiece, well, you know wherever that image forms, you've got to have it inside the 20 centimeters, right? So you can't have a 100 centimeter length between your lenses. That's just simply not going to work, right? So understanding the ray diagram helps to inform how you go about calculating or setting up the physical reality of your system. One of the things I managed to forget to do this morning is get my notes out. And though I might be able to pull this one out of my hat, chances are I'll get something wrong and you guys will be really, really mad at me. Actually, let me try. Let's see how much I actually remember. I haven't looked at my notes today. The magnification of a 2-lens microscope is going to be equal to the normal near point times the length, basically the distance between your objective and eyepiece lens, all divided by the focal length of the objective times the focal length of the eyepiece. Let's see how I did. films, mirrors, eyes. Are you kidding me?
Good spot on.
What did I forget?
The sign.
Uh-huh. Got everything else except the sign. I should have known. I should have just known, right? You'll often, in my notes, I wrote this down as 25 because that's assumed to be 25 centimeters, by the way. So what units are you going to use for like focal length of the objective, focal length of the eyepiece, and for the length?
Centimeters.
Okay. So to be clear, they're not being very clear on this diagram. This length is approximately the distance between the lenses. It's not quite. Microscopes are actually fairly complicated in their geometries. So today we're just going to cheat just a little bit and just do the length, the distance between the two lenses. This magnification equation, okay, I'm going to let you guys fight over this one a little bit in your groups, okay? Because, and I'll explain this a little bit later when we actually get to the lab, but I'm going to give you a challenge, okay? And that challenge is going to be based on this magnification equation and also the magnification equation for a telescope. In general, you can, when it comes to multiple optical systems, you can just multiply the magnifications of the lenses themselves. So like if you know the magnification of your objective lens and you know the magnification of your eyepiece, you multiply those two things together to get the overall magnification of your system. So like in a pair of binoculars, okay, you can calculate the magnification of the objective lens, you can calculate the magnification of the eyepiece, you multiply those two things together, and now you have the overall multiplication. So binoculars are often sold as like 6 times, 8 times, 10 times, and 15 times. Like they're giving you this multiple, right, as a number for how good the binoculars are. In general, really don't go over 8 times unless you know what you're doing. Otherwise, you'll be disappointed for reasons I'll talk about later when we get to telescopes. So at 8 times, what they're trying to say is that the compound magnification of the system is 8. So something that you're looking at probably will look 8 times closer, it'll look 8 times bigger, right? Magnification. But in general, you just keep going and keep multiplying the magnifications together to get the overall magnification. I did forget to mention one thing about magnifying glasses. Right? I want you, so there's actually 2 magnifications for a magnifier. Okay? And the book has got the equations for you. Okay? But most often when you pick up a magnifying glass and you hold something up close to your eye, okay, you can adjust how magnified what you're seeing is. Try it right now. Figure out where you have to put the magnifying glass in respect to your eye, and where how far away do you have to hold things, okay, in order to get like the maximum. You start to see a lot of distortion as you go to maximum magnification, okay. But the other thing that you may or may not notice is that there's some eye strain associated with looking through this device. Okay, your eyes start to get tired. One of the reasons is that whenever you give a human being a magnifying glass and they start using it, they automatically go for maximum magnification. Why is that? This thing is really close. So what is your brain tricked into thinking it needs to do? No. Your brain wants to look at it at the near point. When we put things close to our face, our lenses accommodate for it being close, right? Our lenses tighten up so that we can focus on it up close. When we do this, our brain goes, oh my gosh, that thing's so big, it must be really close to my face. And so you automatically tighten, you automatically accommodate, and you start forming the image at your natural near point. But there's a trick. And it's a trick that requires you to practice quite a bit. It's something I'm used to doing now in any optical system, okay? This trick, by the way, is totally natural when you're using binoculars. Human beings, when they use binoculars and telescopes, automatically relax their eyes. Because what are they looking at? How far away are the things that they're looking at? Infinitely far away. So your brain automatically relaxes. If you can trick your brain into relaxing, into looking through this thing so that the image is not at your near point, but is actually infinitely far away, you can stare for hours through microscopes. I learned this trick early on in college, and the rest of the students in biology class were always confused about how I could just stare into the microscope for long periods of time. It wasn't because I was a nerd. Well, it was because I was a nerd. I understood optics. But it was because I could fully relax my eyes and still have the thing in focus. It's a little bit harder to do with this. It's much easier to do with a microscope that's got a focus knob that allows you to adjust the focus. Because what you do is you close your eyes, you let your eyes fully relax, you open your eyes to a blurry image, and you keep the relaxed feeling in your eyes while you adjust the focus. You don't let your eyes change their focus. You let the mechanism change the focus. What it does is it lowers the magnification by 1. So instead of having 3 times, you might only have 2 times. But in a microscope that's magnifying 280 times, 281 isn't going to get me much more, right? And so just be aware, you're looking through microscopes, you might want to try the trick of figuring out how it works for you, but try to get your eyes to relax. Otherwise, you're just going to get a headache. It's biology anyways, you're going to get a headache. Sorry. There's 4 biologists in my family, so I've got to make biology jokes. All right. Telescope. Okay? So telescopes and microscopes are very close to each other, right? 2 lens systems for the simplest ones, the ones that we'll be building today. But what's the big difference? How far away are the objects for a telescope? Infinitely far away. Which automatically makes the calculation, okay, of where the image forms very easy. Okay? Objects infinitely far away from the converging lens always form at the focal point. Period, the end. Okay? And then we're again going to use our eyepiece will be a converging lens. Notice that where's the focal length for the eyepiece in relation to the focal length for the objective? It's kind of hard. They put a comma right here. F2 comma F1 prime. It's exactly in the same place. So, not only is the image from the objective formed exactly at the objective's focal point, but the eyepiece is placed such that its focal length is exactly at where the image is forming. That gets you maximum magnification. So that means that the length, the distance between lenses is what for a telescope? Exactly. If the eyepiece had a 100 centimeter focal length, if the objective had a 100 centimeter focal length, and the eyepiece had a 20 centimeter focal length, what would be the total length of the telescope? 120. You simply add together the focal lengths, and you know exactly how long your telescope is going to be. In a microscope, you need to fudge a little bit. Okay? Things aren't quite as exact as that. But in a telescope, they are. Okay? The magnification for a telescope, okay, is the focal length of the objective piece divided by the focal length of the eyepiece. And there's a flip in it, so we have to remember our minus sign. So overall, telescopes sort of mathematically easier and conceptually easier to wrestle with when it comes to deciding how they work. This image that they're looking at, right, is also, they're trying to underscore the fact that because of the optics of this, everything forms at infinity, which means whenever you look through a telescope, your eyes are automatically relaxed, which is why people can look through telescopes for a very long time, but microscopes, you get headaches. because they're taught how to do it properly. The type of telescope that we, of course, will be building today and that I'm talking about is something called a refracting telescope that consists of a minimum of 2 lenses, one big one on the front and one smaller one near your eye. You can have more, but in general, those kinds of telescopes don't function very well. So even in very large refracting telescopes, they'll still only have 2 elements in them. If you're ever in the market to buy a telescope, talk to me first. Okay? From the age of 15 to 17, after school, after swim practice, I would go and work for Orion Telescope Company. I was super nerd. Okay? And they paid me lots of money, minimum wage, to talk to people on the phone about telescopes. It was like the best job ever.
You get paid to do that?
Yeah, I got paid to do that, right? What they didn't tell me, because I just wandered in, I would go to Orion Telescope, ooh, the telescope, the production, right? And one day, somebody had come into the store and wanted to buy a telescope, and one of the store people was busy, couldn't help them, and they said, "Hey, kid, do you know anything about telescopes?" I was like, "Yeah." Right? And okay, yeah. This has always happened to me. Is it how I dress? Is it the way I look? I don't understand. People come up to me in stores and start asking me questions.
You seem like a knowledgeable man.
I must this air of authority. I don't know what it is, right? Okay. So people do you work here? They don't even wait for an answer. They say, "Do you work here?" And they start asking me. I'm like, "No, I don't work here." Right? I can tell you more about that thing than the person who works here probably.
They don't look for
Yeah, they don't. I don't know what it is. Anyway, the person walked up to me and said, "Hey, can you tell me about the telescope?" And I just started telling him because I knew everything. I wasn't going to do it. My dad taught telescope making classes at Griffith observatories in the 1960s. Like, I've grown up around telescopes, like astronomy, telescope, the whole 9 yards. And so I was like, "Yeah, right?" And the store person started listening after they were done, came over and started listening, and afterwards pulled me aside and said, "Hey, kid, you want a job?" It turned out that the store person that day was actually the owner of the company. And he said, "Yeah, if you come here after school, after swim practice, I'll pay you to answer questions on the phone for people." And I was like, "Okay." And so I didn't know it. I was too naive. I was a salesperson, right? Okay. But because of my age, there was some sort of like funky thing where they weren't allowed to hire me for like sales or something. Like because people were talking to a minor. Anyway, there's just kind of these weird legal things they had to do. And so I got to talk to people about the telescopes they wanted to buy, but when they wanted to buy it, I had to transfer the call to an adult. Right? And so they would funnel the calls to me for people. If people called up and said, "I just want to buy this thing," they'd do it. But if somebody had a question and all the salespeople were busy, they'd funnel the call to me, and I would just talk to them, right? You go, "Yeah, you need this lens, you need this thing, you want this drive, and this. Yeah, it was. I thought it was great. I've been very fortunate in my life to get jobs where people pay me for doing something I want to do anyway, right? So, except for the time I had served hamburgers. That was, yeah.
What?
Yeah.
What's like next episode?
I flipped burgers and sold Dole Whips. Yeah, in Yosemite National Park. Yeah. In the summer jobs, when I was starting at 14, I got a summer job where I worked in the gift shops and the restaurants and things in Yosemite, and got to run the cash register. And they didn't have the federal government apparently doesn't have laws about minors handling money. Anyway.
Did you have to make the commute then?
To Yosemite?
Yeah.
No, I lived in Yosemite.
No.
I've lived a very privileged life. I understand this. So yeah, no, my father was a ranger in the summer, so our whole family would move up there. And at 14, my mom was tired of dealing with us, and she's like, "You're gonna get a job." So, all for child labor. That was a big tangent. Talk to me before you buy. If you're in a microphone telescope, talk to me because I can tell you about brands. I'm still up on it, right? And the brands that were good back then are still good today. Don't buy them at Walmart. No telescopes. Don't buy telescopes at Walmart. All right. There are other kinds of telescopes, though. Okay. And in the case of refracting telescopes, there is a size limitation for how big you can actually build your telescope. Because you're building the lens out of a physical lens, out of glass or plastic, usually glass, because it's more optically clear. The largest, I think the limit that optical glass can be formed into a lens is, I think it's 1.8 meters is the actual calculated limit on size. Because after a 1.8 meter diameter, the lens itself begins to sag under its own weight. Gravity begins pulling the lens out of shape. And the material they make the lenses out of can't support the weight anymore, and the crystalline structure starts to deform, and you get abnormalities in the lens. So I think the largest actual used refracting telescope, 1.4 meters, something like that. There is a University of Arizona, Tucson, has a kiln for making lenses that big. Like they melt glass and spin it, okay, in a kiln that rotates the entire time they're pouring it, so that they get this even distribution of material. Anyway, it's really cool. So to get bigger, you actually develop a different kind of telescope. In this case, a reflector. So we have a refractor, right, that uses lenses to bend light. This one uses mirrors, okay, spherical mirrors to focus the light. So mirrors are much easier to make. You have a substrate, some structure that is the shape of the mirror. And then all you have to, and that's something, you can make that out of anything, steel, whatever, okay? Carbon fiber, doesn't matter what it is. As long as the surface, one side, can be made smooth, and by smooth we mean optically smooth, so within quarter wavelength of light, and then you coat that surface with your reflecting material. Okay? I make it sound much easier than it is. My entire graduate work was dedicated to figuring out how to do that. But you can make these really, really big. Okay? There's different designs. Okay? This one doesn't work nearly as well as this one does. This is called a Newtonian, because Newton came up with the idea first. Okay? This is called a Schmidt-Cassegrain, named after the inventors, last names of the two inventors, where Newton shoved it out the side, Schmidt-Cassegrain keeps it on the optical axis. And the Hubble Space Telescope is this. Okay? The James Webb Telescope is slightly different, but close enough to Schmidt-Cassegrain that I can lie and say it's a Schmidt-Cassegrain. So you have these huge mirrors, right? And you have some sort of collecting device, camera, or other way to do it. These telescopes tend to be like shorter. The refractors can get really long. These tend to be shorter and beefier, right? Wider. And the wider, the bigger you make your telescope, the more light you can collect. And the more light you can collect, the further back in time, distance in the universe, that you can see. Here is, I think this is a telescope. Is this Mount Palomar? I can't remember. Okay. For scale, that thing right there is a door. Okay. So you can make reflectors really big. Okay. Now, in this particular one, yeah, I'm pretty sure that is a single mirror, single cast mirror, meaning the mirror is one surface. The telescopes in Hawaii on the top of Mauna Kea and Haleakala, they are segmented mirrors, where the mirrors are broken up into honeycomb structures, and each one of those honeycomb structures is its own sort of independent mirror, but then you can computer program the hexagonal honeycomb different segments of the mirror to all work together to be effectively one big mirror. And so in that sense, they can scale that to whatever size they want. I think the Very Large Array down, the ALMA telescope down in Chile, they build telescopes in Chile because there's a big desert there where it never rains. And it's really dry, and it's up high where there's very less atmosphere. I think they have, I think the largest physical mirror they have, it's a segmented mirror, has an effective 30-meter diameter. Really big, like mind-blowingly big. And then they put 3 of those at distances of 3 kilometers apart from each other, and through software, they can build a virtual telescope that has a diameter of like 3.5 kilometers. I go one better. Right? With radio telescopes, which use radio wavelengths instead of visible wavelengths, you can do exactly the same thing, but on a planetary scale. So as long as you've got a radio telescope, say somewhere in Russia, and one down at the South Pole, and a couple here in the United States and Australia, you get kind of this global coverage as far north and south as you can go, in a 24-hour rotation of Earth, all of those telescopes can see the same object, and you effectively get a telescope that has a diameter of 2/3 of the Earth's diameter.
Are those like the big concrete bowl thing?
Concrete bowl, the one in Puerto Rico, which collapsed famously a few years ago, was a radio telescope. These radio telescopes are all over the place. And some of them don't look like bowls, some of them just look like antenna arrays stuck in the ground. It looks like a place where 1970s TVs went to die because there's just all these antennas sticking out of the ground. You're like, what the heck is this? Right? Well, it's radio. Anyway, you can pull off some really, really cool tricks. The Hubble Space Telescope, okay, that Schmidt-Cassegrain design, its primary mirror is 2-point-something meters. So it's like just slightly higher than the average adult size. Again, there was a limitation on how big they could build that because it had to fit in the cargo bay of the space shuttle, right? In the case of the James Webb Space Telescope, quite possibly one of the most amazing engineering feats of all time, because this mirror is something like 4.5 meters in diameter, and it would not fit in the rocket. So what did they have to do?
Fold it up.
They had to build a transformer. They literally had to fold this thing up and have it unfold when it got to where it was going. And it's not in orbit around the Earth, it's in orbit around the sun. Okay? It's actually at one of the Lagrange points between Earth and the sun, but we'll talk about that. The fact that this thing opened up at all, right, is an absolute miracle. Right? Okay? That was an absolute nail biter of a launch. Because with the rocket launch, you're never quite sure. Is it really going to make it? I mean, SpaceX today is making it look easy, but it's not easy. Okay? But they got it out there. Person for scale right there with this thing. And then the James Webb is doing absolutely incredible science. I don't know if you've been following any of this.
The 6 planets they found.
The planets, the distant galaxies is the ones that just excite me, right? They're imaging galaxies that formed like, 250,000 years after the Big Bang. Before the James Webb Telescope, we didn't have anything that was less than, I think it was 100 million years after the Big Bang or something like 4 orders of magnitude younger, right? And I don't know why the media is so surprised about this and why astronomers keep saying they're so surprised about this. But it turns out astronomers might have been wrong.
Wow.
Yeah, I know. This is a group of scientists that's like, ooh, 50% error? Awesome. You can let Mr. X go now. The galaxies that they are imaging, apparently, and I love this, are the wrong shape.
By their standards or what?
How can direct observable evidence be wrong? Right? Like you gathered the photons. It is what it is. What they mean by wrong shape is that their models and calculations didn't suggest that the galaxies would be that well formed that early in the universe's evolution. So now they're having to revise the actual age of the universe. It's a really exciting time to be alive. Some people will be like, oh, gee, scientists don't know anything. You're like, yeah, we don't know anything, but look at the cool stuff we're discovering. We change our minds all the time because we get new evidence. It's really, really cool. Really, really cool. And what you'll be building today is a direct connection to all of that. Alright, I'm gonna stop the recording here. So anyways, because that was lecture, I did record it. Stop it here too.